Hi, I'm Owen, and this is my teammate Bill. Our project replicates and extended a novel X-trend momentum strategy in quantitative finance. I will cover the problem, baseline, and X-trend, and Bill will go over our extensions and results. So the financial markets are non-stationary. When new regime hits, momentum strategy trained on the older data adapts too slowly and will lead to potential losses. And by definition, in new regimes, we only have limited observations to train our model. Thus, we discovered X-trend, which is a few-shot, regime-aware momentum strategy proposed by Oxford scholars that utilize deep learning. According to their research, the X-trend model showed an 18.9% Sharpe ratio improvement over the baseline neural forecaster in trading future contracts. We're curious if this framework can be generalized to the ETF contracts and can cross-asset structure further improve its performance. So our works have three parts involving re-implementing the X-trend model, verifying its performance with different data, and developing extensions to further improve its performance. Our dataset includes 21 index-level ETFs across 5 asset classes, 18 years of daily data from Yahoo Finance, and the inputs are volatility scaled return at multiple horizons and the MACD indicators. The target label is also the next day volatility scaled return. So our baseline is a standard long short-term memory forecaster. It includes a target window plus asset ID through a VSN, then an LSTM, and residual feed-forward layer, outputting positions in a range of -1 to 1. This is a benchmark neural forecaster we need to beat. Our training objective optimizes the Sharpe ratio. It is a return divided by return volatility, and it is a standard risk-adjusted metrics in finance. To maximize Sharpe ratio in training, our last objective is minimizing negative Sharpe ratio with transaction costs included. This is also the metrics we use to cross-validate the model with performance. So the X-trend adopts an encoder-decoder structure. The key idea is cross-attention over regimes. Historical data is segmented by change point detection into shorter regimes, capped by 21 trading days. Each target window retrieves a fixed number of these contacts, refine them with self-attention, and cross-attends to them. So the model is essentially asking, which past regimes look most like what I'm facing right now and can inform better trading decisions. Now I'll hand it over to Bill to our league-like extensions and the results.
After replicating X-trend, we tried extending it in a few different directions. The model on this page uses causal lilacs. The idea is that a target ETF may not just depend on its own history of random historical regimes, but also on what other ETFs are doing. So on top of the context branch, we added a parallel peer branch. Each peer ETF window is encoded with a temporal encoder, and at each target time step, the model only looks at valid peer states from the past. We also use gated residual fusion, so our model only pulls in peer information when it actually helps. And this slide zooms in on the lag-aware attention mechanism. At each target time step, the model scores peer states from valid lags, at a Banach prior, applies both ranking and causal masks, and then keeps only the top K peer lag candidates. This makes the peer lag branch much more selective and reduces noise. Now onto the results. Since the goal is to see whether any architecture is superior, we need to compare models under similar hyperparameters. From running ablations with X-trend, we found that a moderate setup worked better than blindly scaling the model up, which matters in finance because the data is noisy, so adding capacity aggressively tends to overfit. Using those hyperparameters, we run our final comparison. The X-trend model is already very strong, outperforming the baseline neural forecaster in Sharpe ratio. The pure cross-sectional extension actually did worse, which suggests that the pure information without lag awareness is pretty noisy. The more promising extension is to add lead lag mechanism on top of pure cross-section, which yields a Sharpe ratio higher than S&P buy and hold and all the other models. So cross-asset information can become useful once you impose stricter selections. In terms of major takeaways, first, we verify that the X-trend model generalizes pretty well to ETFs. Second, cross-asset information only helps when it's structured carefully. And most importantly, the low signal-to-noise ratio in financial applications means architecture and tuning choices matter just as much as raw model complexity. Going forward, the potential next steps are evaluating larger ETF universes, testing alternative regime detection methods, implementing dynamic lead-lag scoring, and creating more diversified context. And here are the main papers that informed our projects. That includes the original X-trend works and some cross-sectional and lead lag papers. Thank you.